this session. So now we are talking about dynamic programming. We previously solved a very simple problem, which is Fibonacci. We'll look two concepts here about dynamic programming, the memoization technique and the tabulation technique. What we can see here is that basically dynamic programming is an optimization technique when there are sub-solutions, specifically in recursive solutions that are repeated in the recursion tree, right? So dynamic programming basically is an optimization technique, right? It is also specifically designed for optimization problems also, right? That's why it's called dynamic programming. It was developed by mathematicians, not from computer scientists. All right. However, this example, Fibonacci is pretty simple, right? Solving this kind of problems, you can see the power of dynamic programming. So now we are going to face another problem, a real problem. Let me share my screen. Okay, let's see. Okay, this is one, this is two. All right, so again, so this is another problem. Actually, this is a good example in order to show the power of dynamic programming techniques. So let's read. The name of this problem is called count of subsets with sum equal to x, right? So you are giving an array of length n and an index x. The task is to find the number of subsets with equal sum to x, right? So for example, if my input array is 1, 2, 3, and 3, and the another input is 6, so we are looking for find the number of subsets with equal sum to x. Okay, so we have two solutions here. We have solution 1, 2, and 3. The sum of this, the elements of this subset is 6. And the another subset is these two trees, right? The sum is also 6. So there are two solutions. In this case, the input array is 1, 1, 1. The number we are looking for is 1. And the number of subsets with sum equal to x is 4, right? Because each one is equal to 1. Pretty simple. So we need to solve this problem, right? So let me copy these examples. Okay. Any idea to solve this problem?
Maybe we compare the x minus the number of the position in the loop of the array.
Okay. Okay. Any other idea?
Maybe we have to how we say recorrer.
Mm-hmm.
Maybe we have to pass through the array, and here comparing with x, if the position 1 is not equal to 6, we can zoom and the next one, and then until the, the, the zoom don't exceed the x number.
Yeah, okay. So uh, basically we want to know somehow to generate subsets from the original set. And this is basically a combination of the original numbers, right? If this is my input array or my set, these two solutions are subsets from the original one, but also there are combinations from the original one. Okay, so if we think about this, basically what we need to do is generate all the combinations based on the input array, right? So this is a pretty well-known algorithm, right? Because we can start with an empty set, and then we can generate the next subsets based on data. For example, if we consider the last element as part of the solution, so this is the first subset. If not, the empty set is still empty. And again, I'm going to do this again and again with each number. Now the subset is 3 and 3. This still remain 3. This is going to be just 3, and this empty. The number I am looking for is 6. And this subset has a sum up to number 6. So this is a solution, right? This subset is a solution. The solution I am looking for, but there could be more solutions. So I need to explore other paths, right? So let's see. So we have 3 and 3. There is no more solution here. This is just 3, and then 3 and 2. This still is 3, and then is 1, 3, and 2. This is another solution, 1, 3, and 2, because the sum is 6, right? And this is just 3 and 2. This is not a solution. We explore all, and the sum is not 6. So we have only 2 solutions here. This one and this one. And that's all. Right? Okay, any question up to this point? Questions?
No.
Okay, I'm going to simplify this problem, okay? And then I'm going to formalize the recursive definition, because this could be solved using a recursive definition. And then once I have the recursive definition and the recursive solution for this problem, I'm going to use one of the techniques from dynamic programming. Okay.
I get an idea. Sorry.
Yes.
This is Pedro. So I was thinking, you get a x equal to 6.
Yes.
This could be the point to when if you try to use the converging, this will be the maximum number of you are expecting. So if you rest, for example, you start with x equal to 6 as your after first searching. 6 rest whatever kind of these numbers in order to get the a result that at the end be equal to 0, and you will have the set of numbers that each one sum the total of the maximum, that is 6.
Okay, good idea.
Yeah, that's all.
Okay, yes, of course. So basically, instead of generating all the subsets, we're going to just work with the number itself and all the complements.
Exactly.
Yeah, so.
But I think that will work if we only want to find if there is just one subset that sums to 6, for example. But in this case, we need to find all the subset, and when we have the subset, maybe we can use that approach to see if that subset is valid.
You can create like a dictionary in order to say this subset I found, try to find another one.
Let's check. Okay, let's check. Okay, we are starting with number 6 here. Then we are going to generate all the complements based on the analysis of each number. We're going to start from the last element. So the complement here is 6 minus 3 is 3. Okay. I'm going to use the same approach as here. So in each step, I'm going to consider the last element as a part of the solution or not. So if I am considering here the last number as a solution, the new complement is 3. But if I don't consider the last number as a part of the solution, the number is still 6. Okay, and I'm going to do this again and again using the same approach. Now the complement here is 0, right? And once I get a 0, I got my solution. This is one of the solution, this one. And however, I need to explore other paths, right? So this is still 3 here. Now the complement between 3 and 2 is 1. Here it still is 3. The complement between 1 and 1 is 0. This is 1. And now I have another solution, this one. And if I explore other paths, what I'm going to get is a similar number. So let's explore the other paths. The complement here is 2, this is 3, this is the last. There is nothing more to explore. Here is 4, this is 6. Here is 3, this is 4. This is 5, and this is 6. So the other paths finish with a number which is different from 0. So there are no more solutions. The only two solutions are the complements which are equal to 0, right? All right, so we were able to model the problem using a very simple recursive strategy, then we need to implement or figure out the recursive definition. So maybe I can do this in this part. So basically what I am doing is I am looking the solution for a problem of size n, and the number I am looking for is x, right? This is the initial recursive function, right? This could be the first initial call. Then I need to figure out the recursive case and the base case using basically this strategy, right? So basically we have different, we have two base cases here, right? If the number x, right, which is going to be the complement in the next recursive calls, is equal to 0, I have one solution, right? So I'm going to return 1. Else, let me think. So this is a base case, right? An exit case. However, there are other cases. For example, these ones, right? We explore all the possible complements, and still the number the current complement is different from 0, right? So what happens when, for example, if n, this one is going to start, the first call is going to be 4 and 6. N is the size of the problem, right? What happens when n is equal to 0, or basically is less or equal to 0? This is another base case, but this base case basically represents all of these paths, right? The complement is not 0, but we explore all the possible numbers. So there is no solution here. So the return number is 0, right? The return value for this function is going to be the number of solutions we are find out for the inputs array and the value of x, and that's all. Because if you look in detail, the problem is asking the number of subsets. It's not asking about which elements conform the subsets. It's asking just the number of subsets, the number of solutions, right? So these both base cases should be enough to define the recursive definition. Now I need to figure out the recursion step. Okay, so let me think. The recursion step should be something similar to this equation. Okay, so let's think. As you can see here, okay, let me change the color. As you can see here, we are starting with a current complement, which in the initial step is just the number x. In the next step, we are computing the complement. If we are considering the current element as a part of the solution. If not, the complement will be still the same. So basically, we have two recursive calls here. Once with the new complement, the another one with the same complement, right? So let's write here. So basically, we're going to look the previous number, n minus 1. And the new complement is basically x minus, so this is going to be the array A at position n. So this is going to be the first call when the complement, when we are considering the element at position n as a part of the solution, right? And the another one is going to be the previous element, but with the same value of the complement, which is x. And that's all. Right. So let me think. The only thing I need to consider is that this complement should be always valid, right? This should be always positive. So this part is always called when x is greater than the value at position n. So if this happens, I'm going to call this. In other case, I'm going to call this. Something like that. Any question up to this point before I start coding the solution? No questions. Okay, so let me be clear. This analysis is very important, because if you don't do this analysis, write the actual code is going to be difficult, right? The formal analysis, the mathematical analysis for this kind of problem is very, very, very important. Okay, so let's write the code. Con subsets. We have two inputs, a and x, and that's all. We want to do this. This is the array. This is the val x, and we need the length of x. So this is a, this is the length of the array, and this is the value x. So a is equal to this, right? So this is n, and that's all. This is the definition, right? The only thing the only two variables that we're considering now is okay, let me be clear. The only variables that is going to change in every recursive call is the last two variables from this function, n and x. But variable a will always be the same because it's their input array, right? So let's write the solution based on this recursive definition. Basically, if x is equal to 0, there is one solution. If n is less than 0, there is no solution. Else, every other case, we are in the every other case is the recursion step. The recursion step, let me think, it's going to be just x. The recursion step, we have these two calls, so we need to do. So I'm going to write this as as function f in order to match this part, the formulas with code. So this is going to be just a n minus 1, then x minus a at position n. So let's think about this. This is wrong because the length of a in this case is 4. But what I need to do is to work with indices. So this should be minus 1. Okay, now this is correct. But this call is going to be valid only if the value of x is greater than the value at position n. So this is the value for the first call. Okay. The another call is going to be similar. F n minus 1 with the same current complement. The return value is going to be just f1 plus f2, something like this. This should be the solution. All right, so let's think about this, right? So what I try to do is to translate the formulas into code, right? So let's think about the recursive definition. So this is right, this code is right, this code is right, this code is right. Look at this. Basically, we need to do these recursive calls and then sum the values from them, because each recursive calls could be a solution or not, as you can see here. For example, this path, if we are using this path, there is a solution. But in this path, we are not considering this as a solution, but still there is a path with a solution, which is this. That's why we need to sum the number of solutions from both calls, right? Then let's think about this. The last value of n is when it's negative. If it's negative, there is no solution. This should work. Let me test. Okay, where is the, okay. Okay, it says it's printing 3, which is wrong. It's wrong. So let's think what's happening. Let's see what's happening. Okay. This is fine, this is fine. Okay, so this should work. This is fine. I can do is just print the values in each step. There's a number 2 here, and there's a 1. Okay. What's happening? Any ideas? Let me check again the base case. So maybe let's check. The base case is this. If the complement is 0, the output is 1. This is right. If the current element is less than 0, there is no solution. This is just 0. If value, okay, so this is an else case. Okay. Why? Okay. Let me clear all of this. Okay, okay, this is working. This is not. All right, it's not working. So let me do something, right? So this is a good, actually this is a good exercise. So what I'm going to do now is I'm going to print the solutions. So if I do that, I'm going to have more details about the solution and also about this little bug. Okay, in order to do that, I'm going to use another technique which is called backtracking. And basically, what I'm going to do is to store the paths from each recursive call. Okay, so I'm going to start with an empty array at the beginning, and then in each step, if I consider this as a part of the solution, so this is wrong. Actually, let me think. No, this is right. So this is going to be part of the solution, and this is not going to be part of the solution. And then I'm able to print here the paths. Solution. Okay, let me think what's happening here. This is fine, this is fine. Oh, this is not fine. Here. Happening. Here. Okay. All right. So what's happening? We have the two solutions here, 3 and 3, and 3, 2, and 2. And these both are repeated solutions, right? Yes, they are repeated solution, but actually this is an edge case because 1, 2, and 3, this is one solution, but 1, 2, and this 3, this is another solution.
Yes.
Yeah, because it's a different tree, and the another one is 3 and 3, which is this. So the solution is right. Solution is right. Let me think. Actually,
the output says 3.
The output says 3. Yeah, that's my fault. Actually, the solution were always right. Okay.
But we learned something else.
Yeah. That was my fault. But however, we learned something new here. This technique is called backtracking. And what I'm doing here is I am storing the path of each recursive call, right? So when I got the solution, which is in this base case, I am printing the solution. right? That's why I'm getting here that not just the number of solutions, but also the subset itself, right? Okay. Now this is a good opportunity to do the analysis, the runtime complexity and the space complexity. What do you think? It's not easy to analyze this problem. Actually, it's more difficult than Fibonacci, but it's not impossible. Okay, so let's start. This is 1, 2, 3, and 3. We are starting with 6 here. This is basically what we are doing is this. We're generating a tree with this format, right? Right? Do you agree with this? Right? If we want to know the runtime complexity and space complexity, we need to analyze this recursion tree. Okay. So let me think. So in order to get the space complexity, all we need to do is analyze the height of the tree, which in this case is very simple. Basically is ON, right? In the worst case scenario, the height of the tree is not going to be more than N, and that's all. However, in order to generate all the subsets, we are doing a lot of recursion calls, right? In the first step, it's going to be 2 power 1. In the second step, it's going to be 2 power 1. Here is going to be 2 power 2, 2 power 3, and lastly, we are going to have 2 power n, right? So, in the worst case scenario, the number of leaves in the recursion tree is going to be proportional to 2 power n. And this is the runtime complexity for this algorithm, which is expensive.
Exponential.
It's exponential. You're right. And if we use the previous analysis from Fibonacci, maybe we can use one of the approaches from dynamic programming. And maybe we were able to reduce this runtime complexity, which is itself huge, into something, for example, like this. We don't know, right? But the first thing we need to do is analyze the recursion tree and then look for repeated solutions, right? So this recursion tree is not trivial, but what I'm going to do now is going to believe that there are some repeated solutions in this recursion tree, right? And then I'm going to use this information in order to reduce the runtime complexity of this problem. Okay. So let's start. Okay. So the initial runtime complexity is 2 power n. The space complexity is n. And then we are going to reduce this cost using a dynamic programming technique. As we previously did, we are going to use the memoization technique. So this is going to be my cache variable. And the first thing what I'm going to do is, if the first question using the memoization technique is always if I previously solved the problem for the current input, right? So if I already solved, what I need to do is just reduce the solution. However, I need to identify the key, right? In the previous example, the solution was stored at position n. However, this function has many other variables, right? And what we need to do is identify each recursion call as unique call. Okay, so in order to identify the key, or in order to identify each recursive call, we need to use these two inputs, n and x. Do you agree with that? Any questions? This is a good opportunity to ask because this is something new. Okay, again, in order to store the solution into this cache variable, what I need to do is identify each recursion call, which is this and this, as unique. And the only variables that are changing in each recursion call is basically n and the variable x. If you see here, it's the only two variables. This one, the path, is not part of the solution. This was another technique that I used to print the solution, but it's not part of the recursion definition itself. Okay, so this is the first step of the memoization technique, reduce. And another step is to store the solution itself. So basically what I need to do is, this is my final solution. What I need to do is store this solution into this position and return F. That's all. So again, what I'm doing here is storing the current solution, right, which is this F, into my cache variable at position key. Position key is a tuple, which is formed by n and x, and that's all, right? If I run again this, it should still, oh, it's not working now. It's printing, no, it's working.
No, it is working, but it's just that you already solved one. So you have to
Sure. Yeah, so it's working here. It's printing the same number of solution, but it's not printing one of them. So what it's saying is that it was previously stored into the cache variable. So there is no need to explore that subtree into the recursion tree. And basically that was what we are looking from the beginning. So this is a good optimization. If we do again the analysis, we're going to get a good surprise. So let's do again. So if I need to, so let me think. Let me think. So in order to do the analysis, the big connotation analysis for this new solution, what we need to do is to focus on the cache variable, right? So this cache variable is a dictionary, right? Initially, it's an empty dictionary, but then we are storing certain keys. These keys are basically a pair of numbers, right? For each pair, we're associating the solution for this key, and that's all, right? we can think about this this variable memo as a big matrix. Why? Because we're storing here, our key is a pair. So if it is a key, it could be a matrix, right? But the matrix size is going to be this, right? The size of the input array times the number we're looking for. In this case, it's just m times x, and that's all, right? So let's start just analyzing the space complexity. The space complexity, it will be proportional to O m times x. Do you agree? Why? Because in the worst case scenario, this dictionary is going to be proportional to a matrix of size n times x, right? So we are paying for this optimization in space complexity. But let's check the runtime complexity. Runtime complexity, all right, so this is going to be tricky. So let me think. So this is the key. So it's, yeah, it's not, the analysis is not going to be part of the code. Actually, it's going to be part of the recursion tree analysis. So basically what we are doing here is that instead of exploring all the paths from the recursion tree, we're exploring just few of them, right? And the number of recursion steps is going to be proportional to the size of my dictionary. Do you agree with that? Why? Because the first instruction into my solution is this check, and my last instruction into my solution is this step, right? So this first condition is basically a condition that controls the number of recursion calls into the recursion tree. And this is going to be always proportional to this size, n times x. So that's why the runtime complexity for this new solution based the memoization technique is also n times x. Because in the worst case scenario, the number of calls we are going to do from these two recursive calls is going to be proportional to the number of solutions which are stored in memo, and that's all. And this is a huge improvement from exponential to polynomial. Any questions?
No, just like a comment that
Yes.
how that all that you are showing us is amazing, because the first approach that we use that was exponential, tremendous exponential.
Mm-hmm.
So as with this solution, we are allocating in memory variables, like using dictionary techniques,
Mm-hmm.
and how using this technique we can improve the performance in the computing systems.
Mm-hmm.
That's great.
Yes, you're right. And that's why dynamic programming is amazing.
Yeah, because Fibonacci series is a series, arithmetic series,
Mm-hmm.
that is infinitive. So It's described the ellipse, concentric ellipses that never end. So, but we can modulate using these techniques until a certain level of exploring, and it's great computing solutions like this.
Sure. Sure. So guys, this is the end of the class of today. Obviously, there is a iterative solution for this problem, right? So maybe we are going to do this next class, but this is a good exercise for you also. You can write this as a iterative solution using the tabulation technique. And if you analyze the runtime complexity, it will be very clear that both the runtime complexity and space complexity is proportional to this polynomial cost, n times x. Okay, so I'm going to stop this. We're at the end of the class. This is a good opportunity to ask something related to this class or something related to any other thing. Any questions?
I had one, Alexander. Sure. I began the program with Talently when you had in the third class. But I don't know if in the first classes you show how we can transform our code or iterations into a mathematical function to that we can analyze the complexity and space complexity. And at this time, I can it's a little bit complex for me to transform the line of the code to the mathematical expression.
Sure, it's not. Yeah, it's not easy, that part. Actually, we did it in the first classes, but it was just few examples. And the key, basically, as you saw in this class, is know about recursion, right? Recursion thinking is the key, not only to solve problems like divide and conquer. It's very important to face this kind of problem with dynamic programming. The only way to improve your skills facing these kind of problems is solving as much as possible famous recursive problems, like, for example, Hanoi, Fibonacci, let me think, sorting algorithms like quick sorts, merge sorts, right? Well, which have a recursion definition. Yes.
Okay.
All right, so I am looking for...
Alexander, hi.
Yes.
I have a question about the Fibonacci exercise. You can share the exercise of your code.
Yes. I'm going to share both solutions, the Fibonacci.
No, but I wanted to ask about the code.
Okay. Okay, I'm going to share my screen again. All right. What's the question?
Okay, in the
subsets,
in the tabulation techniques. No,
Yeah,
in
here.
Fibonacci.
Okay, here.
You say that the space complexity is O n of n.
Yes.
Why do you save the value of 0 and 1 if is in the array? If you have you know that the values are the same. Maybe it's repetitive that you save the values in the array, and you have the answer that if the n is equal to 0 is n, and n is equal to 1 is 1.
Okay, I didn't follow you. Maybe we can just switch to Spanish. Español.
Okay. No, te decía que, o sea, tú dices que la complejidad, no, que la complejidad de espacio es de 0 de n, ¿no? En este caso, pero, o sea, porque estás guardando n valores en ese array, pero es necesario guardar los dos valores de f de 0 y f de 1, si es que ya sabes que la respuesta es 0 y 1 respectivamente, ya no es necesario, ¿no? Guardarlos.
Sí,
Entonces, quizás
es
la
muy buena.
complejidad de
Muy
espacio
buena.
sería
Uno.
n-2, ¿no?
No, de hecho, hay una solución que tiene un costo O de 1 de espacio.
Ah, ok.
Y el costo runtime sigue siendo n. ¿Ya? ¿Por qué? Porque yo puedo crear dos variables aquí.
Ajá.
Así, y puedo decir la nueva variable es igual a f de 1 y f de 0, ¿no? Y mi nueva variable acá va a ser f de 2. Y esto va a ser siempre válido si es que, déjame pensar, este es el nuevo, necesito guardar el anterior. El f de 1 va a ser igual. Creo que sería algo así. F de 1 es el nuevo f de 1 y el f de 0. El f de 0 va a ser un TMP y el TMP va a ser igual al anterior. Y esto va a ser así, ¿no? Simplemente usando variables anteriores, yo puedo reducir mi complejidad a un costo de espacio O de 1. No necesito los arrays. Pero eso ya no es programación dinámica, es una optimización basada en los requerimientos del problema.
Ok.
Okay.
O sea, hay muchas soluciones para este problema, básicamente. Lo que estás tratando de decir.
Sí,
Un montón.
Exactamente, eso es lo que estoy tratando de decir.
Ok.
Sí.
Chévere.
Ok, les he compartido el feedback form por Zulip y por el chat de Zoom. Estamos al final de la clase. Tomen su tiempo para completar el formulario. Y si tienen alguna otra pregunta más, este es buen momento para hacer. Otra cosa más, en las siguientes secciones, las últimas secciones, vamos a hacer desarrollar otro tipo de teoría. Ya, seguramente si es que ustedes han pasado por procesos de entrevistas, ya no todas las entrevistas están relacionadas a código, o sea, resolver problemas de este tipo, sino muchos otros problemas o entrevistas técnicas están relacionadas a pasar case interviews, ¿no? Que son problemas de system design. Generalmente te ponen un problema con algunas restricciones y requerimientos únicos y tú tienes que resolver, pero no a nivel de código, sino a nivel de, a veces, arquitectura, a veces de diseño, de software, diseño de componentes y ese tipo de cosas, ¿no? Case interviews. Clásicos.
What could be improved?
Alexander,
Sí.
yo una duda. Esta es mi primera vez también aquí con ustedes y otra cuestión que incluso que estábamos viendo sobre estas soluciones. Una plataforma que conozco donde se presta demasiado a realizar como soluciones de este estilo es HackerRank. ¿Me recomiendas en esa plataforma seguir realizando soluciones o tú conoces algún otro donde sea también mejor para aprender este tipo de cosas sobre algoritmos, cosas así, estructura de datos?
Ok, entonces, yo he estado viendo este de acá, el de Interview Cake, que uno de sus compañeros lo compartió. Está bastante bueno en realidad. Yo diría como información complementaria, incluso como referencia teórica está bien, porque tiene los problemas que con mayor frecuencia vienen en entrevistas de trabajo, ¿ya? ¿Y cuál es la razón por la cual recomiendo esto? ¿Cuál es la razón por la cual recomiendo este tipo de plataformas? Porque ya tiene los problemas seleccionados, ya tiene problemas tipo que sabes que tienes que practicar, pero en plataformas tipo HackerRank no tienes esa selección, ¿no? Tienes un montón de problemas, quizás no sabes por dónde empezar.
Sí.
¿No? Y así en LeetCode también hay, ¿no? LeetCode. Para mí o sea, ambas plataformas son válidas, ¿ya? La manera de, digamos, hacer efectivo tu estudio y tu camino en algoritmos y estructuras de datos es seleccionar los tipos de problemas que deberías enfocarte, ¿no? Entonces, por ejemplo, acá, el de programación dinámica, ¿no? Dynamic Programming. Dynamic Programming, Memorization, Bottom-up, a ver, estos problemas son clásicos. Making Change, problema de las monedas. Este problema es un clásico. ¿Ya? Se aplica a programación dinámica. Esto es algo que deberías ver sí o sí, si es que te metes de lleno en programación dinámica. Este problema es otro clásico. ¿No? Y así.
Okay. Muchas gracias.
Sí, entonces la ventaja que tenemos acá en las sesiones es que ustedes pueden ver estos problemas, ¿ya? Y con algunos días de anticipación, semanas de anticipación, ustedes me pueden enviar los problemas que quieren que resolvamos en clases, y los resolvemos, ¿ya?
Ok.
Sí, la única desventaja que yo veo en este tipo de plataformas es que no te explican, ¿no? No están ahí alguien en vivo que le puedes preguntar las razones de las razones de las razones.
Ok.
Sí.
Hay una plataforma que se llama Algo Expert.
Algo Expert, sí.
Sí, y hay videos que explican cómo desarrollar los problemas.
Sí.
O bueno, ya si no lo...
Algo Expert es otra plataforma que yo recomiendo, que es como este de acá, como Interview Cake, pero además de eso tiene videos, ¿no? Sí, súper recomendado también. Si quieren practicar inglés, también, los videos son buenos. Ahí están los videos. Y
¿Esas páginas son gratis o tienen costo?
Hay algunas que son gratis. Este Interview Cake, por ejemplo, si tú tienes una cuenta de desarrollador GitHub como estudiante, tienes 2 meses, creo que gratis. Y así hay algunas plataformas que son gratis y que tienes ese tipo de acceso.
El otro de algo
Expert, algo Expert sí cuesta $100, me parece.
¿Cuánto lo pago?
Ahora sí lo del compu.
Sí, cuesta un poco. Bueno, señores, estamos al final de la clase. Por favor, no se olviden de completar el Fitcore Form. Y nos vemos la siguiente clase.
Muchas gracias.
Chao, chao. Hasta luego. Hasta luego.
Cuídate, chiquita.
Chao.